Good evening, everyone. I welcome you all to live session number 8 for week 8 for the course Non-Conventional Energy Resources. The course instructor for this course is Professor Pratap Haridosar from IIT Madras, and I am his TA, Amit Kumar Sharma. So, like every week, today also we will discuss about the week 8 course content. In first initial slides, we will revise the course content of week 8. Then after that, based on the course content, based on the lectures of week 8, we will solve some sample assignment questions. And I hope that those sample assignment questions will be helpful for you in your current assignments or maybe in future assignments. So today we will cover about the wind energy. As we have some part of wind we have already covered in our previous classes. So today let's start with the week 8 course content. Again, I welcome you all. If you are having any issue in the viewing the slides, okay, let me know in slides or sound anything. Please let me know. So the first thing is so the first thing is theoretical limit for the wind power. Okay, so as we cannot use the fully we cannot use the full wind power. There is a theoretical limit based on the energy principles. So so there is a Bates law in 1920. Bates is a scientist name. So he gave a law. According to that, there is a theoretical limit. So theoretically, we can only get up to that wind power only. We can tap off only a particular power from the wind energy. So there were two assumptions. First is the wind fully stopped by the windmill. Second one is wind unaffected by the windmill. So based on the calculation in our further slides, we will see the some calculations. So the data is 16 upon 27. So it comes to 0.59. So there is a theoretical limit of 59%. Okay. So whatever equipment is, whatever windmill is, whatever are the conditions, anything, you cannot get more than 59% of wind energy. Suppose your wind is having 100 watt of energy, then you can only tap off around 59 watt energy. Okay. So you can only tap off 59% of the total available wind energy. Okay. But practical efficiency obtained is around 10 to 30% of energy originally available in the wind, because we are having some other efficiencies. We are having efficiencies due to the some part and the location, and there are various other things also. So this is a maximum. So mostly we are getting 30 to 40% of efficiency, or sometimes 10 to 30% efficiency. So it's important. 16 by 27. It's a very important number. You should remember this. So this is called Bates limit. 16 upon 27, or you can say 0.59. This is a Bates limit. So we cannot get more than this efficiency from the windmills, or you can say the wind turbines. So we know the Bernoulli equations: half rho v square plus rho gh plus p equals to constant. So this is the P is the static pressure. Rho g is again uh, its rho is constant, g is constant, as its height is also constant, because we are taking the wind as a particular height. So this is also constant, and it is a potential head, you can say. It's a dynamic pressure or dynamic head, that due to dynamic. Okay, the half rho v square, velocity is included. So this part equals to constant, because we are dealing with the wind turbine, so the height is fixed. So rho gh can be also considered as the constant. So you can transfer the rho gh to the right side and merge with the constant. So you will get half rho v square plus p equals to constant. Okay. So this we can say the dynamic pressure plus static pressure are constant. So this is the basic equation, that half rho v square plus p equals to constant for the wind energy calculation. Okay, so further we will see it. So these derivation covered very well in the course class. Okay, so for detailed explanation, you can refer the class notes or you can refer the class videos. We are just briefly looking toward the derivation. So suppose this is a control volume, you can say, and here is the your blade is here. Okay, this area, this side you can say like V1, and this side you can say the V2, and these are section that are just far behind this near the blade, so it can consider as infinity. This one also like infinity. Okay, so based on this, we can apply the bundle equation on different parts. Okay, so the first is half rho V1 square plus rho infinity equals to half rho V square plus pressure before. So it is before the wind turbine pressure, and P is the after wind turbine pressure. So for the after case, half rho V square plus P after equals to half rho V2 square plus P infinity. Okay, so now subtract these two. So we get P before minus P after equals to half rho V1 square minus V2 square. So now for force, because it's pressure, so we know pressure equals to force upon area. So for force, multiply with pressure with the area. So force will be A multiplication with the P before minus P after. So we will get half rho A V1 square minus V2 square. Now we also know the change in momentum is rho AL V1 minus V2. So the force is rate of change of momentum. So just do the derivation of this. So you will get rho A small v V1 minus V2. So this is, you can say, the with respect to the L. Okay, the derivation with respect to the time with the for the L. Okay, so it will convert to the V. Okay, so now we are having two forces from this equation, equation 1, from this equation, equation 2. Now equate these two. Rho A V V1 minus V2 equals to half rho A V1 square minus V2 square. So we will get the velocity at the blade, it will be half V1 plus V2 by 2. Okay. So these are the basic, these are the calculation. The kinetic energy will be half rho A L1 V1 square minus half rho A L V2 square, because the one side is velocity is V1, other side is V2. Okay. So power will be dE by dt, and E is the kinetic energy. Okay. So do the derivation with respect to T for the energy. So you will get this equation half rho A V V1 square minus V2 square. So the kinetic energy of kinetic energy of wind for away for the windmill will be, you can get, you can put the value of V here. Okay. So when you put the value of V, so you will get this equation. Okay. After solving, I'm coming to the final equation. You will get this. P upon P naught equals to half 1 minus alpha square plus alpha minus alpha cube. So alpha is the ratio of V2 minus V2 upon V1. Okay. Now for the maximization, if you do the derivation with respect to alpha, the solving we get alpha value is equals to minus 1 and 1 by 3. So minus 1 is not possible, so it will be 1 by 3. So alpha will be V2 upon V1, and V2 upon V1 equals to 1 by 3. Okay, so for the maximum value, this will be this. Okay, so we will get like this graph for P upon P naught to the alpha. So you can say the first is increasing up to certain point, then decreasing. This point is the V2 upon V1 equals to 1 by 3. So now from this point we find the bed's limit. So you can say the change in energy in wind. Okay, we have already seen this. power extracted from wind, P d by dt. Okay. So the kinetic energy in incoming wind half mv square. M is the mass, v is the velocity. So half rho v, velocity is v1. So velocity will be sorry, v is a volume of air. So it will be a into L, area into the length for the particular section. Okay. So the power in incoming wind will be for P naught half rho a v1 cube. So it's important to note that the kinetic energy of the wind is proportional to the velocity square, but the power is proportional to the velocity cube. So remember it, it's useful. So kinetic energy, or you can say the energy of wind, is proportional to v velocity square, and the power is proportional to the velocity cube. Now, like further solving for alpha equals to 1 by 3, we will get 0.59016 upon 27. Okay. So P upon P naught equals to 16 upon 27. So this P is power, this P naught is the power in the wind, P is the power generated from the wind turbine. So P will be maximum of 0.59 of P naught. So there is a theoretical limit of maximum power is 59%. So this derivation have already covered in the class notes. So you can refer the class notes and you can refer the videos. Okay. So based on the data, we can draw this graph. So power from the wind, power from the windmill, or upon the power in the wind, the power available in the wind. So P upon P naught. On the x-axis, we are having V2 upon V1. So we can draw this graph. Okay. So a particular value of V2 upon V1 equals to 1 by 3, or you can say 0.33. It will be here. So this will be maximum 0.59. Okay. Before, if ratio is less than 1 by 3, it's increasing, and after this point, it's again decreasing. Okay. So this graph is also very important. So the conclusion from this part is that the Bates limit indicates that only about 59% of the energy available in the wind can actually be captured. So this is very important, that we can only capture about 59% of energy available. Okay. And the actual efficiency will less than this limit. This is a theoretical limit, but when we are considering the other efficiencies of other equipments also, then the actual efficiency will be less than this limit. Now we will see wind turbine parts. Wind turbine is made of different parts. Okay. So briefly we will cover some parts, and you can see here a basic diagram of wind turbine. Okay. So this is a basic diagram of a wind turbine. From the diagram you can see that it's a horizontal axis wind turbine. Okay. Axis is the horizontal. So this is a horizontal axis wind turbine. So there are various parts, they are named. Okay. So the first is rotor. You can see the rotor. This part is rotor. Then the blade. Then tower. At the bottom you can see. One is the power cable. We are getting the power from the generator. Okay. There is a brake, gearbox, nacelle, and the anemometer, controller, generator, your drive, and your motor. So there are different parts. So briefly we will cover every part. Okay. So the first part is blades. So lifting style wind turbine blades. So there are different types of blades. So one will be lifting style wind turbine blades. These are designed most efficiently, especially to capture the energy of strong and fast winds. Okay. Some European companies actually manufacture single blade turbines. Turbine can be made using one blade, two blade, or three blade, and a number of blades. So We will cover in our further slides that what is the main important factor for designing the blades. Okay, number of blades, and we will see that. So no, normally we design the number of blades as per our requirement. Okay, the rotor. Second, the one is the rotor. The rotor is aerodynamically designed to occupy the maximum surface area. Okay, the blades are lightweight, durable, and corrosion resistant material. So the blades should be lightweight because the wind turbines are installed in open environment, and it's also on a huge height. So if it's heavy, then we require like very strong tower, so it will increase the cost and increase the complexity in installation. So blades should be lightweight. If they are lightweight, then maybe the rotation of the blades will be high as compared to the more weight. They should be durable and corrosion resistant material. The best materials are composite of fiberglass and reinforced plastic. So the best material are composites of fiberglass and reinforced plastics. Nacelle is a housing which contains all the components which are operate the turbine. So basically, this complete housing, you can see this complete housing in which all the components are installed or are placed. That is called nacelle. So it is mounted on the top of a tower and includes gearbox, generator, low and high speed shafts, controller, and brakes. So these are the major equipments which are included in the nacelle. The nacelle is fitted with a wind and a wind vane. Nacelle provides housing for lower speed shaft, brake, gearbox, high speed shaft, generator, anemometer, and wind vane. So these are the major parts that are housing in the nacelle. Now a gearbox and coupling, or you can say the transmission system. A gearbox magnifies or amplifies an energy output of the rotor. The gearbox is located directly between the rotor and the generator. A rotor rotates the generator as directly by the tail vane. So as we know that these wind blades are in very large shape, okay, maybe the 15 meter or 20 meters the length of the each blade. Okay, so the rotation of the wind blades are low as compared to required for the generator. Because if we want to generate electricity from the generator, then the generator shaft should be at very high RPM, but the wind turbine blades are rotating at low RPM. So we need a system that can convert the low RPM to high RPM. So we are using this gearbox. Okay, so you can see the shaft. You can see these blades are connected to the rotor, and the rotor is connected to a shaft that is going here. You can see, and that is connected to a bigger gear, and this bigger gear in connection with a small gear to the generator. So when the shaft rotates, this big gear rotate, and the small gear, that is a small dia. So for one rotation of this gear, the shaft attached to the generator will having more rotation. So in this way, we can control the rotation using gearbox. We can design the gearbox for our requirement. Okay, so we can convert the required RPM of the shaft to of the rotor to generator. Now the controller. So the controller realizes the wind direction, wind speed output of the generator rotor, and other required performance quantities of the system, and initiates appropriate control signal to take appropriate corrective actions. So controller is very important part also, because uh, today we know that all the things are controlled automatically. So best the controller is the, you can say, the brain of this wind turbine. So it will like decide it will decide all the things like what should be the direction of this. Okay, because from the your drive and your motor we can also control direction based on the which gear should it run, what is the speed of rotor, and which gear we should require. Okay, because we need some, you can say, the high constant RPM for the stable electricity. So based on that, this controller control all the parameter and performance quantities. And the seventh one is electrical generator. So this unit produce electricity from the rotation of the rotor. The generator comes in various size with respect to. This generator converts mechanical energy into electrical power. So we know the generator converts the mechanical energy into the electrical power. We all know the output of the generator coupled to the load or system grid. So the generator is generating the electrical power from the mechanical power that is received from the this rotor main shaft. Okay, and you can see the power cable is attached to it. So from that generate electricity using this power cable, we can transmit this electricity to the grid. Okay, or to the required location. Supporting structure. So supporting structure, you can say the tower or itself. This is a heavy structure set up with a proper foundation and carries all the components of the windmill. So it should be a heavy and proper structure, should able to sustain all the weights of all the equipments, because you can see the blades, the rotor, nacelle, gearbox, all are very high in weight. So the structure should be strong and sturdy enough to handle all the weight. Otherwise, it will break. So it should be properly designed with a proper factor of safety to withstand a dead load of all components and wind force. Because we know that if high velocity wind is there, then more wind force will be there on the blades and the system. So the structure should be able to sustain all the dead load, that is the load of all the components, and also the wind force that is dynamic. It can vary. So we should design the tower for a good factor of safety. Okay, so in worst case scenario, if the wind speed is very high, so that the structure can sustain all the loading condition. So here we can see the cost to weight ratio for the rotor, nacelle, gearbox, generator, and tower. So, so the rotor and generator is having maximum cost to weight ratio as compared to the nacelle, gearbox, and tower. Tower is the lowest cost to weight ratio. Now the rotor blades. So rotor blades are made of steel, maybe aluminum and composites. It should be lightweight. Okay, the blade should be fatigue resistance. Okay, because we know that if there are three blades. Okay, there are three blades, and this is tower installed. Okay, so when a blade in front of the tower, okay, then that blade will then that blade, because the tower is behind that blade, so the force on that blade will be different if the tower is not behind the blades. Okay, so there will be high loading, high stress loading, and low stress loading. So there will be, you can say, the cyclic loading type phenomena will be there. So there should be fatigue resistance among the blades. Otherwise, fatigue failure will be there. Fatigue means, you can say, the component will fail before the design loading. Okay, it should be the blade should be strength, so it can sustain the loading. Should be stiffness, high. Should be high stiffness, so the integrity of shape. So the shape of the blade will not change if the wind force is very high. Shape will remain same, remains same. The environment, it should be the lightning, humidity, temperature. The material of the blade should be like, so that it can sustain the lightning, the humidity, and the temperature, and various environmental factor. Blade recycling. So blades material should be such that if when the wind turbine complete its life cycle, so that we can recycle the blades, and we can make new blades out of it, or we can use that material. Okay, so the material should be recycle, uh, should be able to recycle. Okay, so these are some important points regarding the rotor blades. Okay, first it's steel. It should be steel, or you can say the aluminum or composites. Lightweight. It should be fatigue resistance. It should be have good strength, good stiffness, environment friendly, like it can sustain the lightning, humidity, and temperature changes. And the blade material should be recyclable. Now the tower. So regarding the tower, it should be the able to handle the wind shear. Okay, variation with the altitude. As the altitude vary, the wind speed vary. So the wind shear will be there. So the tower should be able to sustain the wind shear. Doubling the height increase wind speed by 10%. Okay. So if the height is double, the speed is increasing 10%. And we have already covered in previously that power proportional to V cube. Okay. So if your height is doubled and speed is increased by 10%, then the power will be increased by more than 10 to the power cube to more than 30%. Okay. So power will be increased by 30%. So the small change in wind speed causing a large change in the power. So it's very important because the tower because for the increasing the height you just need to install a strong sturdy tower only. Okay, if you are able to install a long sturdy long tower, then you are getting more power. Doubling the height requires 4 times of diameter. If you are doubling the height, then diameter requirement is also more. The material choice impacts transportation and construction cost. Yeah, it's whatever material you are choosing, you should also consider the transportation and construction cost. The conical tubular steel towers are quite famous. The concrete increase life. You should increase the concrete also. So it increase the life and better for taller towers. It will give the good strength for up to 40 or 40 to 50 years. So it will be very good for the wind turbine life cycle. You can today with the help of technology we are using good also for the tower design. The hub. So the blades directly bolted onto the hub. So hub is the part where all the blades are bolted. Blades bolted to pitch bearing, which is bolted to the hub. So blades bolted to the pitch bearing. So there is a part pitch bearing. So pitch bearing. So the blades bolted to pitch bearing, and pitch bearing is bolted to the hub. Okay. Now the gearbox. So the gearbox connects the shaft from the blades to the generator. So we have seen in the diagram that gearbox is connecting the rotor shaft to the generator. The low RPM of blades to higher RPM of generator, because generator require higher RPM to generate the electricity and the blades are having low RPM. So with the help of gearbox, we can convert the low RPM to the high RPM. Today, there are gearless direct drive designs also considered. Research is going on this sector also. So if you are using the direct design, like you are not using the gearbox, so there the speed fluctuation will be there. Okay. So more magnets required for desired frequency. So suppose you require a particular frequency of electricity. So then if your RPM is less, then you require some other parameter. So you have to generate the more magnet, you have to apply the more magnets. Okay. So the more magnets will be required for the desired frequency. Neodymium, it's a rare earth material. It's required goes up a factor of 10. So if you are using the gearless drive, then the use of this neodymium will be increased by the factor of 10. And it's a rare earth material, so we need to consider uh, this area because it's increasing the cost, and also it's a rare earth metal, so difficult to procure. So we need to look into it, and it's the size and the it will also heavier because you know that more magnets required. Okay, more magnets required. So 10 times of neodymium is required. So the weight will increase so much. So based on the increased weight, we also look into the tower design and all other aspects also. So whenever we have to design, we have to check all the parameters. Okay. Now general materials which are used in the windmills. So for the rotor, glass fiber reinforced plastics are used. Okay. So because we require high strength and fatigue resistance, so this glass fiber reinforced plastics give the high strength and fatigue resistance to the rotor and blades. Nacelle or like your drives blade pitch change. Nacelle is used for the only your drives blade pitch change, coolants, brakes, bearings, shafts, controllers. Okay, these are housing these parts, and it's made of steel or aluminum. So for gearbox, we are using epicyclic gears. Okay, and the research is going on to get eliminating the gearbox, but the size is also increasing. Okay, generator, we are using permanent magnets or copper windings. Tower, it's pre-stressed concrete or steel. We are using pre-stressed concrete or steel for manufacturing the tower. Is my screen visible? Anyone, if there, please confirm. Is my sound is coming? Am I audible?
Yes, sir.
Okay, my PPT is also visible, na?
Yes, sir, it's visible.
And can you see the pointer also? Marker and pointer?
Yes, sir. Both are visible.
Okay, thank you. So the conclusion is that the modern wind turbines have several parts and these are integrated in a design that places specific requirements on some of the parts. So based on function, a wide range of materials are used for the parts of a modern wind turbine. Because more research is going on the wind energy because all over the world we are focusing on to the increasing the renewable energy part in our main energy supply. So we are looking towards the renewable energy sources. So the wind energy is a major part in that. So we are focusing on various different blade designs, materials, and how to increase the efficiency. Because as of now, we know the theoretical limit is 59%, but with the current technology, we are only achieving 10 to 30% of efficiency. So the research is going towards to increase the overall efficiency and go as near as we can to the 59%. So research is going in that area. Okay. Now the tip speed ratio. So this tip speed ratio is also important part. So it's represented by the lambda. Okay, so lambda is let's say the velocity of tip and the velocity of the wind. Okay, so tip this is the tip, the last point of the blade. Okay, from the rotor. This is the rotor. Okay, the blade is attached here. Last point is tip, and this part can be considered as the radius. Okay. So when the blades are rotating at angular velocity omega, so the linear velocity will be v will be if the angular velocity is omega, so v will be omega r. So the tip speed ratio is lambda equals to v tip upon v wind. Okay, so v can be omega r upon velocity of wind. Okay, if the velocity of wind is more than this tip velocity, then what will happen? The lambda will be less than 1. If the velocity of the tip is more than velocity of wind, then lambda will be greater than 1. The value of lambda is very important when we are considering the wind turbine design. So this type of a aerofoil structure you can see. So it's a lift design. Okay, so the wind is flowing across the this. Okay, so you can consider two sections. You can see the one or two. So the wind is going like this. So there are 2 points before the airfoil. So and after when the 2 points are coming, then the velocity will be different on both side at the up and the down, because you can see the upside. This air particle has to cover more distance as compared to the lower path. Okay, so if they are coming at the same time of point on the outer side, so it means that the upper part is traveling with a higher velocity, okay, as compared to the lower part. Okay, so the velocity of the upper part will be higher as compared to lower, so there will be pressure difference across the top and the bottom. So the pressure will be more at the bottom side as compared to the upper side, so the lift force will be generated and this will try to go in upward direction. Okay, so in this case the tip velocity is more than the wind velocity. For more uh, for more detail around this calculation, you can refer the professor's class notes. So the lambda will be equals to v tip upon v wind. Okay, so the tip velocity is more in this case as compared to the wind velocity. So the lambda value will be greater than 1. Now there are two types of turbine: horizontal axis turbine and the vertical axis turbine. Okay? So for this turbine, the V tip is greater than the lambda is greater than 1. Now for this turbine, we will see. Okay. So for the vertical axis turbine, you can see this is the design. So the major role is here is the drag force. Okay. In the in the horizontal axis turbine, the lift was working there for the rotation of the blade, but in this case, the drag is the playing main role in the rotation. So you can see that if the wind is flowing like this, so more air will come in this, and so this air will push this part of blade. Okay, in this direction. So the blades will be rotating in this direction. Okay. So in this case, the velocity of wind will be more as compared to the tip velocity. So the lambda value will be less than 1. So you can say for the lift design, lambda will be greater than 1, and for drag design, lambda will be less than 1. Okay. Now you can see in this way we can arrange the number of blades. Okay. So here are 3 blades, 2 blades, and 1 blades. So if the 1 blade, then the velocity will be very high as compared to this, and as compared to this. So the wind tree is also an alternative design. Okay. In we can we can in a tree shape we can design it, and this every rotor will rotate. Okay. It also look good and can generate good amount of power. So the conclusion from these slides are that the lift based design more efficient than the drag based design, and lambda is greater than 1 for lift based design. For power generation, RPM is important because generator works on the RPM. Okay. And even one blade may be sufficient. For other mechanical purpose, torque is important, and multiple blades may be desirable. So if we only looking for the RPM, then we can go for one blade that will have more RPM but less torque. If you also require torque, then we can have more blades. So the torque will be there and the RPM is also there. So it depends on the requirement and the other components available design. The third one is interesting alternate designs are available for wind energy capture. So we have seen that this tree design. So it's also very interesting. Okay. In this way, we can design different of wind turbines. Now let's see some questions. The first one is the formula for calculating the wind power. So what is the formula for calculating the wind power? Okay. Just take 2 minutes and try to remember. We have covered in our slide, the professor have also covered.
Sir, is it half rho A V1 square minus V2 square?
Half rho A and
V1 square minus V2 square. Is it for force or power? I'm not remembering.
Yeah. You need to know the power. So I have already mentioned that power is proportional to V cube. Okay, so the basic you can compare the units of all these options. Wind energy is proportional to V square, but the power is proportional to V cube. So now try to find out the correct answer. You can find out in which option there is a V cube is possible.
In third option, half rho AV V1 square minus V2 square.
Yeah, right. So this option is correct. So the correct answer is half rho A V bracket V1 square minus V2 square. For detailed explanation, you can see the previous slides and the class notes. Okay. So we can discuss briefly. Option A will be not correct because you can see the half rho AL V1 square minus V2 square by just knowing. If you're not remembering the complete derivation, if you know this, that power is proportional to V cube, so you can balance the units. So in this we can see that power is proportional to V square only. Okay, because A is area, L is the length, so there is only V square is there. So it will be wrong answer. Now second is again half rho A V1 minus V2 square. Again you can see that power is proportional to V square in this option, so this will also not correct. Now in this option we can see that V and V1 square minus V2 square. So there are for velocity there are three parts. Okay, so the total unit will be 3. So here the power is proportional to V cube. So it can be a option. Let's check other option, fourth option also. So it's half rho A by T V1 square minus V2 square. So this A by T will not velocity because we know V is will be dx by dt, or you can say the dl by dt. So distance with respect to time, but area with respect to time will not give the velocity. So it's also proportional to V square only. So from the all four option, we can conclude that option A, B, and D are proportional power proportional, giving the result as P proportional to V square. But we know the power is proportional to V cube. So only option 3 is giving this result. So the correct option will be option 3. So the complete derivation maybe you will not able to recall instantly. So just try to remember these key results. Based on these key results, you can apply the basic fundamentals and you can find the answer. Is it clear?
Yes, sir.
Yeah. Okay. So the correct answer is half rho A V bracket V1 minus V2 square. Question number 2. The bed's limit is the space maximum efficiency for a wind turbine. According to it, only space percentage of kinetic energy from the wind can be used to spin the turbine to generate electricity. So basically, in this question, we are talking about the bed's limit. What is the efficiency and what is the result of bed's limit? So take 2 minutes and then give answer.
Second option. It is the theoretical maximum efficiency and 59.3.
Yeah, uh, we will check. Let's wait for one more minute because some people will. Actually, I'm giving 2 minutes for every question because whenever able to join today, maybe they will see the class tomorrow or day after tomorrow. So at home they can try to solve this question. That's why I'm giving 2 minutes. Okay. So again, I'm again explaining. In this question, we have to just tell the bed's limit. Okay. So what is the bed's limit? We have already seen the complete derivation. Based on the derivation, we have come to a conclusion that there can be only there is a theoretical limit. Okay, up to that limit only we can capture the wind power. Okay, wind energy. Okay, so that limit was 16 upon 27. But in the options, we have written in the answer written in decimal form. You have to convert it into decimal. It will come around 59.3. So theoretical limit is 59.3%, and it was given based on the theoretical principle, not by the experimental principle. Okay, it was given by the basic energy conservation formulas. Okay, based on the based on the basic theory. So Betz was the first who gave this limit. So that's why it's called Betz limit. So Betz limit is the theoretical maximum efficiency for a wind turbine. According to it, only 59.3% of kinetic energy from wind can be used to spin the turbine to generate electricity. So the correct answer will be B. A will be incorrect because it was not experimental, so it was incorrect. Again, experimental incorrect. Option D is saying theoretical, but data is 49.3. But we know, you can remember 16 upon 27, it will come to 59.3. So this option is also incorrect. So the correct answer is B, theoretical, and 59.3. So this is the correct answer. Question number 3. If V is the velocity of the wind, if V is the velocity of the wind, energy available in the wind is proportional to. Just read the question carefully. What is mentioned, it's energy or power. Don't confuse between those terms. Both are different. Okay. So based on that, try to find out the answer. If V is the velocity of the wind, energy available in the wind is proportional to option A V square, option C V cube, and V4. Just take 2 minutes and give answer.
Should be V square.
Yeah, V square. Okay, we will see. So just try to remember it's asking for energy. Okay, so V is the velocity of wind. So whenever there is a velocity, okay, and we have to find out the energy, then the first thing in our mind comes to the kinetic energy. Okay, so based on the kinetic energy principle, maybe you can relate the options. So we know the kinetic energy is half m v square. Okay, so wind is flowing with a velocity v, and there is some mass of wind. Okay, so we can see the energy is proportional to v square. Okay, if it was mentioned, if suppose it would mention the power, then it will be v cube, but it's mentioned as the energy, so the correct option will be v square. Option A will be incorrect, C will incorrect, D will incorrect. So correct option is v square. Now, question number 4. If the wind velocity is 20 kilometer per hour, then the tip velocity can be 60 kilometer per hour. Is this statement is true or false? And what is the reason? Uh, in which case it can be, like for horizontal turbine or for vertical axis turbine? Let's take 2 minutes and try to give answer. You can think about the tip ratio. Try to recall the value of lambda. What is the lambda? And for which turbine it is greater than 1 is less than 1? You can recall that. Based on that, you can answer this: is it true or false? Know that the lambda is V tip upon V wind. So for one case it is greater than 1, for one case it is less than 1. So try to recall for which turbine it was greater than 1 and for which it was less than 1.
For lift type, it is greater than 1.
Okay, for lift type it was greater than 1. And lift type turbine is come under which category? Horizontal axis or vertical
Horizontal
axis?
axis.
Yeah,
Horizontal axis.
horizontal axis. Okay, so it comes under the drag category for vertical axis. Okay, so if the V tip, or you can say tip ratio is greater than 1, suppose this ratio is 3. Okay, so the V tip upon V wind equal to 3. So the tip velocity will be 3 times wind velocity. Okay, so if the wind velocity is 20, then the tip velocity can be 60, because lambda is greater than 1 and lambda equals to 3. So based on this calculation, it is possible. It's possible, then the statement is true. Okay, so don't confuse that how the tip velocity can be greater than this, because by the design of aerofoil structure and the blade designs and all the design parameters, it can be possible. The correct answer is true. Question number 5. The question is, windmills are usually positioned, option A, such that the tips of the adjacent windmills touch each other. Option B, such that the base of adjacent windmills touch each other. Option C, such that there is sufficient space between windmills to avoid air turbulence from one windmill affecting the adjacent windmill. Option D, such that the gears of the windmills touch each other to increase efficiency. Take 2 minutes, recall the basics of windmill designs and all the data, and try to give the answer.
Sir, third option.
Option number 3 is that there is sufficient space between windmills to avoid air turbulence from one windmill affecting the adjacent windmill. Yeah, it looks correct. Let's see. Just wait one more minute. Let's check if any other option is also correct or not, because it is not mentioned here that only one option is correct or more than one option is correct. So just a simple reminder, in any question, in any assignment question, if it is not mentioned that only one option is correct, maybe there are more than one options are correct. Okay. So in that case, if you are in hurry and you just answer only one options and you think your answer is right and you will get the full marks, so it is not the case. Just check all the options, try to mark all the correct answers. Only then you will get the full marks. Otherwise, you will get partial marks. Okay. So try to remember this. Just check the other options also. Maybe they are correct or maybe not. But you have to check all the option and you have to be confident for the answer.
Third is the only best answer.
Yeah. So let's see from the option 1. The first option is such that the tips of adjacent windmills touch each other. So just try to visualize this. If the tips are like adjacent and touching each other, then it will be very difficult for the windmill to work. There will be very less space and they will not work, or maybe there will be some accident also. Such that the base of adjacent windmills touch each other. If the base are touching, then you can remember the blades will be strike each other, because if you know that if this is the tower, then there is a radius, okay, of the blades. If the base are touching, it means the both blades will be touch each other also, so the windmills will not run. Such that there is sufficient space between windmills to avoid air turbulence from one windmill affecting the adjacent windmill. So it looks right. Yeah, it is correct. Okay, so there should be
Right.
sufficient space so that every windmill will have sufficient wind velocity and there will be no air turbulence. The fourth one is such that the gears of the windmills touch each other to increase efficiency. It is not physically, it is not feasible, because we know that every wind turbine is having the gearbox attached to that self. If we are connecting all the gearbox from some shaft or some configuration, it is not feasible and it will be not, because the wind turbines are on a large height. It is not possible also. So this is also not correct. So the correct option is option C. The correct answer is option C only. Now the question number 6. The gearbox is used in a windmill to typically ensure. So we have to tell that the gearbox is used in windmill to typically ensure. So we have mentioned what is the basic purpose of gearbox in our initial slides. So let's see the options. The option number 1 is uniform RPM at blade and generator, higher RPM at blade, lower RPM at generator, low RPM at blade, higher RPM at generator, and no RPM at blade but low RPM at generator. Just try to think, try to imagine the wind blade speed and try to imagine the basics of generator. Okay, at what RPM we are getting the electricity. Just take 2 minutes and try to answer.
Lower RPM at blade and higher RPM at generator.
Yeah.
Correct.
Low RPM at blade, higher RPM at generator. Let wait one more minute if anyone want to answer or anyone want to think about the answer.
Okay, right.
How about option one? It's also going to be matching the RPM, the gearbox basically.
If the RPM is matching, then why we need the gearbox itself? We can directly connect the shaft to the generator. We don't need a gearbox.
Usually, Hardas has told that the gearbox is going to be obsolete.
Okay, but in practical case, if the RPM is, that's why the absolute na. So the designer will omit that gearbox because the gearbox is not performing its task, or that is not in the use. So if you are installing the gearbox, if you are suppose if you are generating the electricity at the RPM of the blade itself, then
Yeah.
if you are installing the gearbox, then it means you are increasing the weight, and the gearbox is no use. So that's why if we go for the design, then we will eliminate the gearbox.
How about the drag type in which there is a higher RPM?
In drag type,
Of course, it is common to the windmill, right? Windmill can be of both types.
Yeah, both types.
So
It can be.
both are possible. What I mean to say is second and third both are correct, or uniform RPM.
Second and third, or you mean to say the first and third?
First is universally required,
Okay.
and the third is considering the lift type.
Second, but I think
You,
the higher
you see
RPM,
that
the drag
the
type
drag
can the drag type can generate high RPM also.
But you know, that's why what was there in the lecture, if you recall, and what I recall is that there are going to be something like more magnets will be added in the generator itself, and the gearbox will be a direct train. There is no gears.
Yeah,
Gearbox.
more magnets will be added in the case if you want to generate the electricity at the
The
frequency
lower,
at the
yeah.
lower RPM. Yeah. So you have to match the frequency. That's why you will add the more magnets. Okay. Yeah. But the velocity of the blades will be higher in the lift type. In drag type, we know the lambda value is less than 1.
One.
So in this case, the velocity of the blades will be no higher. Okay, it will be lower. So in this case, you absolutely need the gearbox. In the lambda is greater than 1. Okay, so based on the design of the number of blades, we can get the higher speed. So at the higher speeds, we can generate the electricity by just configuring the generator. So that case is possible. And so it is possible only with the horizontal axis turbine, not with the vertical axis turbine. Okay, because the lambda is 1. So this option will be higher RPM at blade, low RPM at generator. So it will not correct because generator requires higher RPM. Okay. Yeah. So the main purpose of the gearbox is to increase the RPM. Okay. Because that is under research. Because if you are increasing the value, increasing the magnet, that is fine. But that is a part of research. We are looking forward toward it. But as of now, we are not using those options. Okay, because we have to use the rare earth materials that are not easily available, and the cost is also very high. That's why we are just using the basic gearbox. Okay, and we are the low RPM at the blade will be converted to the higher RPM at the generator. So the correct option will be option number 3. So whenever there is a design, it's not only for wind turbine. if any design engineer is there, so there is a cost economics is a very important role in any design of system. Okay, if you're designing any system, then the engineer, then the management, and everyone is working toward to optimize the system design. The optimization is for to minimizing the cost and maximizing the efficiency. So that is a major role playing in any design. Okay, so that's why the gearbox is playing a very important role, because gearbox is having a lower price. We can easily install it. It's already a proven technology. We can convert the low RPM to higher RPM. Okay, that's why we are using the gearbox, and it's easily available. The cost will be also low as compared to the other part that we have to increase the more magnet and all. Maybe if the that part in future will available at a lower cost, maybe with some other material we can generate that all the system, we can set up all the system, then maybe we will go to that part. Okay, so the correct option is option C, lower RPM at blade, higher RPM at generator. Now come to the option number 7. Select the statements which are true. The statement A, tip speed ratio is ratio of the linear speed of the tip of the blade to the wind speed. The tip speed ratio is greater than 1 for push design and it is smaller than 1 for lift design type windmills. The tip speed ratio is smaller than 1 for push design, or you can say the drag one, and it is greater than 1 for the lift design type windmills, and the speed of the blades is more at the center than at the tip. So check all the 4 options. It's given in the question that select the statements. It's not statement, it's statement. So maybe more than one statements are correct. Maybe the more than one options are correct. So try to check all the options and answer. Just take 2 minutes.
Sir, option A and C.
Yeah. Okay, option A and C. Okay, we look into this. For hint, just try to recall the tip speed ratio formula. Okay. So those who are attending it maybe will attend in future, or we will see the recording, so they can try to recall what is the formula of the tip speed ratio. Okay, we have covered in our previous slides for the vertical axis turbine and horizontal axis turbine. So it is called lambda. Okay, so for the one value is greater than 1, for the one value is less than 1. So based on that, you can find the correct answers. Let me write lambda is equals to so this is the formula. Now try to find the answer using this tip speed ratio. Okay, so check the option number 1, option A. So option A is tip speed ratio is for the is the ratio of linear speed of the tip of the blade to the wind speed. So we know that lambda is v tip upon v wind. This is the linear speed of the tip and this is the speed of the wind. So yeah, this option statement A is correct. Statement B is tip speed ratio is greater than 1 for push design and it is smaller than 1 for lift design. We have covered already the lambda is greater than 1 for lift type, lambda is less than 1 for drag type. it is saying that the speed ratio is greater than 1 for push design. So for drag, or you can say the push, it is less than 1. So this statement is wrong. Check option C. Tip speed ratio is smaller than 1 for push design or drag design, and it is greater than 1 for lift design. So yeah, we know that lambda is greater than 1 for lift, lambda is less than 1 for drag. Option C is also correct. Check the option D. Speed of the blade is more at the center than at the tip. So center, we know that there is a rotor is there, or you can say hub is there. All blades are attached to this rotor. So is it possible that the velocity at the center is more than the tip? No. Okay. So at the speed of the blade is more at the tip side. So this option is also wrong. So let's see what are the correct options. So A and C. Okay. So the answer are A and C. Come to the question number 8. The question is, what is the significance of 3 blades in windmill? Option A, in comparison to 1 blade, 3 blades are used to increase the interaction with the wind. Option B, better suited for generating high torque. Option C, distributes the load on the shaft more uniformly than 1 blade windmill, especially with respect to wind turbulence near tower. Okay. So try to recall the class notes and our previous slides and try to find the answer. Take 2 minutes.
Should be B and C both.
B and C both. Okay, we will check. Try to think about A also.
All three A, B, C are correct. I feel so.
Okay, just wait for 1 more minute and then we will discuss. So the question is, what is the significance of 3 blades? Okay. So we have covered about the blade should be having fatigue resistance and it should be sturdy and strong. Okay, so we have also uh, discussed about the fatigue and cyclic loading. So think in that area that if there are more number of blades, then maybe there will be less cyclic loading, or maybe the stress will be relieved on the blades due to the design consideration of 3 blades. Okay, try to think in that way. Okay. So the option number A is, in comparison to 1 blade, 3 blades are used to increase the interaction with the wind. So yeah, if the more blades are there, then it means they are capturing the more wind. So the more interaction, they are having the more interaction with the wind as compared to the single blade. So this option is correct. Second is better suited for generating higher torque. So if three blades are there, mean the speed will be low as compared to the single blades. Okay, if the speed is low, it means it is having higher torque. Okay, and three blades are there, then they will generating more torque also. More torque. Okay, the speed will be less as compared to the single blade. So yeah, it's also correct. Better suited for generating higher torque. The third one is distribute the load on the shaft more uniformly than one blade windmill, especially with respect to wind turbulence near tower. We have covered this, I think. This is the tower. Okay. So if you are only having one blade, so when this blade is at the position this to a position A and position B. Okay. So when the blade is option position at A as compared to position B. So at the position B, the tower is behind the blade, and position A, there is no tower behind the blade. Okay. So due to the tower behind the blades, the velocity of the air is having some changes here. Okay. And at A side, it will different. Okay. The loading, the force by the wind will be different on both A and B locations. So the loading on A and B will be different. So it will make a cyclic loading, and cyclic loading will be reason of the fatigue failure. Okay, so we don't want this type of loading. So what we will do? We apply three blades. So now what happened? Now there are three blades, and the blade is at position B. Then there are two blades. Okay, they are balancing the loading. Okay, so every time whenever a blade is in front of the tower, then there are two blades to balance the loading. So they will balance the loading, and in this way the loading will be more uniformly as compared to one blade. So the distribute the load on the shaft more uniformly than one blade, and windmill, especially with respect to the wind turbulence near tower. So yeah, option C is also correct. So the conclusion is that option A is correct, B correct, and C is correct. So all three options are correct. So the correct answer is A, B, and C. Question number 9. The horizontal axis wind turbines. Options are excess stronger winds are often mounted on tall towers. Usually have blades that are pushed by the wind for only part of their rotation. Capture wind energy throughout rotation. Just take 2 minutes. Try to go through every option and try to answer.
All four are correct.
Okay, we will see. Take 1 more minute to go through the options. Go carefully.
Sir, except the third, all are correct. They are
Okay,
lifted, not pushed by the wind.
okay. So we are having two answers. One is saying all four are correct, and the other is saying three are correct except option C. So just take 1 more minute to more carefully analyzing all the options.
Sir, the first option is totally incorrect. Rest three are okay.
First option
Because
is incorrect.
yes.
Okay. We will look
talking
into it.
about horizontal axis wind turbines. Stronger winds, there is a lock, if I recall correctly.
No,
Which
if you recall correctly, then it's not mentioned on the
there,
stronger wind. The speed is mentioned. Try to remember the speed. At a particular speed, the lock will activate. But whenever we are mentioning the stronger wind, so what is the definition of stronger? It is not defined. So you cannot put this into that category actually.
say beyond 30 kilometers per hour.
Yeah, no. After 70, there is a lock.
Yeah.
But
So
yeah.
stronger winds means it can be a turbulence which is more than 120, say
No.
120 kilometers per hour. So what will
No.
happen?
Just
The turbines will get damaged.
Yeah. Your point is correct. But the main point is that the option is access stronger winds. So is it mentioned the wind velocity here? Please tell me yes or no.
They don't mention it, but stronger winds definitely means
No.
it
You
is beyond the
cannot
capacity
actually,
of
you
handling.
cannot, whenever a question is there, you cannot assume. Okay. If there is a, in maybe in the question, they will mention the stronger means this range, the medium mean this range. Okay. If there is range mentioned in the question, then only you can assume the data. If you have given a question, okay, in that question there is no mention that what is the meaning of stronger winds, so directly you cannot assume that the stronger wind means the wind having 70 km per hour velocity. Okay, so we cannot assume that directly. So if the question is not mentioning anything about the stronger winds definition, then we cannot assume directly. Now just again rethink. Take one more minute. I'm just, this question is little complicated. So just take one more minute to think. So I think for option one, I have cleared the doubt that it's not for this question only, it's for all questions anywhere. We cannot assume anything beyond that question. Okay, if there is, you can say the Newton's law, or some fundamentals are mentioned, then it's okay. But we cannot just assume the data like for stronger or medium. Okay, maybe for some question they will mention the range, like they will define the range, like for stronger wind means 70 to 80, lighter wind means 10 to 20. If they're defining these ranges, then we can choose the appropriate options. But if that is not given, then we will not think in that perspective. Okay, we will think that stronger winds mean high velocity winds. So okay, let's discuss the answers. So the first one is access stronger winds. So yeah, this option is correct because horizontal axis wind turbines, we are having three blades or more blades. Okay, and these are a higher. These are located on a high tower. Okay, the radius of blades are also high, so they can handle stronger winds. So option one is correct. Option second are often mounted on tall towers. Yeah, it's also correct because horizontal axis turbines are mounted on tall tower. Okay, tower in the range of 80 to 100 meter, maybe more than it. Okay, it depends, maybe around 60 meter, 60 to 100 tens of meter. Okay, usually have blades that are pushed by the winds for only part of their rotation. Yeah, I think one of you was saying that this option is correct. So just again, just reread this option. Usually have blades that are pushed by the wind for only part of the rotation. So this by the definition pushed and by the part of rotation. So we can see, we can, if we compare this with the horizontal axis turbine, then we can find out that in this turbine, every blade is having interaction with the wind in all rotations. Okay, every time they are having interaction with the wind. It's not that for the one cycle, one blade is interacting with the wind and other two are not interacting, and maybe two blades are interacting or other one is not interacting. So this is not the case with the horizontal axis wind turbine. So this part is also not true. Second, pushed. So we know the horizontal axis turbine best work on the lift. Okay, it not work on the drag concept. It work on the lift concept. So it is also false. So based on these data, we can see they usually have blades that are pushed by the wind for only part of the rotation. So that is possible for the vertical axis wind turbine, because in vertical axis wind turbine, we're having blade structure like this. So one blade will be pushing, but other blade is having not taking part in the rotation. Only one blade is taking part in the rotation. So this statement of option C is correct for the vertical axis wind turbine. So this is wrong for given horizontal axis wind turbine. Is it clear?
Yes, clear.
Yeah, okay. Now the option D is capture wind energy throughout the rotation. So yes, as we have already discussed it, that in the horizontal axis turbine, all the blades are having interaction with the wind all the times in every rotation. So they capture wind energy throughout the rotation. Option D is also correct. So let's see the correct answers. So the correct answers are access stronger winds, are often mounted on tall towers, capture wind energy throughout the rotations. So A, B, and D are correct. Question number 10. Where and why is the pitch bearing used in windmill setup? So it's about the pitch bearing. Options are blades are attached to it. Hub and blades are linked using this. It reorients the blade. It increases the RPM. Try to go through all the options. Try to think about the pitch bearing. Okay. Try to recall the previous classes or today's class. Take 2 minutes to answer.
Option B and option D is correct.
Option B and option D. Okay, we will see. Meanwhile, you can go through other options also. Maybe they can also correct.
Option B and option C.
Option B and option C. So today we are having conflict between the candidates. Okay, let's see.
A is also correct.
Again, we have a new answer.
A is also correct.
Yeah, okay. Try to go through all the options. Take 1 more minute because we are having conflict among the answers. Let's see.
Okay, option B, C, D. All three.
Option B, C, D, but you were also saying that option A is also correct. Just
No.
10 seconds back you were saying option A is also correct. So both options should I
No,
consider from your side?
I have never said. I have never said. I have said option B and option D before.
Option B and D. I think someone else said that like A is also correct. Maybe.
I have told A and B.
Okay, okay.
I'm sure about A and B.
A and B. So okay. So we are having three answers. Okay. So who is saying A, B, and D? Please mention your name. Okay. How many persons are online? Anyone? Who is? What are the answers?
A is not correct.
Please tell me one by one. Okay. Please, the first answer. Anyone?
Not correct.
First is correct.
First is correct. Okay. We are having two opinions. One is that it is not correct, and second is that it's correct. Anyone want to answer? Any other?
Sir, first is not correct, I think.
First is not correct, you think. Okay, so you are having doubt. Okay.
I'm sure first is cannot be correct.
First cannot be correct. Okay. Uh,
Pitch bearing is a part. Pitch bearing is a part which joins the hub and the blade.
we join the hub and the
Blade.
blade. Okay, okay. So where and why is the pitch bearing is used in the windmill setup? So pitch bearing is the pitch bearing is part of the hub or not?
No, no, it's not part of hub.
Hub is separate. Blade is separate. Both are joined, linked by pitch bearing.
Okay. Actually, the correct options are blades are attached to it, hub and blades are linked using this, and it reorients the blade. So we all agree with the option B that hub and blades are linked using this. Yeah, correct. It reorients the blade. We agree. It increases the RPM. Yeah, I think one of you said the option D is also correct. So it is not, because the RPM increasing is depending on the gearbox. Okay. So gearbox is increasing the RPM. So for option D is wrong, totally wrong, because the gearbox is increasing the RPM. Now what about the option A? Blades are attached to it.
Yeah,
So
that is obviously required.
that is,
Blades are attached to the pitch bearing, and pitch bearing is attached to the hub.
yeah, yeah.
So that is how
Because
it is. Now you can say hold by one hand, and you say hold something like you can add
yeah,
one
yeah,
more
right,
part
right.
in this.
So
So
when
both
when
are
you
like
yeah, so when you are
it's so
saying that,
confusing.
yeah, when I think all of you saying that option B is correct. So just think about that. If the option B is correct, then why option A is not correct? If hub and blades are linked using this, then it means that they are attached to the blades. Now blades are attached to it. Option B is correct, and option A is automatically correct. So option A, B, and C are correct. Actually, pitch bearing blades are attached to it. Hub is attached to it. It's a link between the blades and the hub, and it reorients the blade. Suppose, suppose,
Actually, if you
no, you
what
are
I
saying
wanted to
that,
say,
yeah,
I wanted to say the
hmm,
question word by word. If you read and say why, where, and why is
yeah,
bearing used.
hmm,
So uh, where where means it is between the two, and why it adds to the reorient the blade.
okay, okay. But
That
it
is only the
reorient,
two things.
yeah, no, no, it reorienting the blade. It means na blades are attached to it. If blades are not attached to it, then how it will reorient?
That is basically the first thing which should be there.
Yeah. So
Like
that's why I was saying that just re-go all the options. Okay.
yeah.
So I think today's class is very very good actually. We are having different opinions. Yeah, it's nice to interact with you all. Yeah. So I think now it's clear to you. Is it clear to all of you?
Yes, yes,
Actually,
clear.
yes, sir, it's clear. The question number 5, in which you are talking about the energy linkage with the velocity.
Yeah, question number 5. No, you mean to say question
Five or
number,
six? No, not
yeah,
yeah.
3,
Before,
question
yeah,
number
this
3.
one,
Yeah,
three.
yeah.
Sorry, three.
Mm-hmm.
So, like you say it's not kinetic energy because energy is available. See, v is the velocity of the wind, and we have and Mr. Haridas they proved it. He proved it that the v, the energy is energy from the wind is related to the velocity with the cubic ratio. And he has
No,
used the
no.
examples,
No.
and he
I
has
was
proved
saying
it
that,
also.
yeah. He proved, but that was power, for power. Again, power. Don't confuse between the power is the rate of no, energy per second, the delivery of
Mm.
energy per second. So power is
Yeah.
connected to the V cube. That is the catch in this question. Okay, we are the
Power is
energy. Yeah,
energy.
yeah.
Okay,
So
okay. I got this.
yeah,
Yeah.
d by dt is the power. Okay,
Yes,
so
yes,
d
yes,
by
yes.
dt proportional to V cube. But the energy
Yes.
is the kinetic energy only, na, in the wind. So that is
Yeah, yeah.
proportional to V square. Okay.
dl by dt, that will make it
Yeah.
another v.
Another
Right.
V, right. dl by dt, another V.
So,
So that will be proportional to V cube. So that's why I stressed in our, I think, slide number 4 or 5 maybe, that
yes.
don't confuse between
Now,
the energy and power.
mm,
Okay.
got it. Got it, sir. Thank you so
Okay.
much.
Okay. Thank you. Now let's come to the other questions. We are having some more questions also for you. Yeah. So these are quiz, true and false. So the first one is the blades of the windmills experience cyclic loading and hence must have excellent fatigue properties. Let's take 1 or 2 minutes.
True, sir.
Always should be.
Okay. Let's wait for other answers because today we are having different opinions. So it's very interesting today. Let's see any other opinion is there or not. Let's wait for 1 more minute. The question is the blades of the windmill experience cyclic loading and hence must have excellent fatigue properties. So we have covered this in our the requirement of material for the blades and why the three blades are using. We are using three blades normally. Okay. So we have covered in our our in revision segment and our in question segment also because one question was related to this. So try to recall those and try to answer. Is it true or false? Okay. So the blades of windmill experience cyclic loading. Yeah, as we have covered already that because if in the we are having a tower. Okay. So if one blade is crossing the tower and when it is opposite to the tower, so at the both locations the blade will have different loadings. Okay, so that will form cyclic loading and cyclic loading will create fatigue, and in fatigue we know that the the material fail before its design limit. Okay, so we don't want to introduce fatigue in our material. Okay, so we want to balance the loading, so the cyclic loading will be not there, and it is there then the effect is very low. So that's why we design the blades accordingly. So it is true statement actually. So the blades of winds will experience cyclic loading and hence must have excellent fatigue properties. So the material should have good fatigue resistance or fatigue strength. So it is true statement. Option B, question number 2. Bed's limit represent the minimum efficiency that a windmill must have to be commercially successful. Read question carefully, try to recall the notes. Bed's limit represents the minimum efficiency that a windmill must have to be commercially successful.
False, sir.
False,
Okay,
false.
okay.
Should be maximum.
Yeah, it should be maximum. Yeah. Let's see, just wait for one
Question
more
is
minute, maybe. So, so uh, whenever we see the bed's limit, so the first thing should come to our mind is that bed's limit mean 16 upon 27. So try to remember this figure, okay? 16 upon 27. So the bed's limit is a theoretical maximum efficiency. theoretical maximum efficiency. Okay, this represents that the only this much of amount we can capture from the wind energy. It's a so for the windmills or wind turbines, this limit is very important. It's a very fundamental. Okay, so it's represent the maximum theoretical efficiency. Okay, so the question is, where this limit represent the minimum efficiency? So from the statement, it's incorrect because it represent the maximum theoretical efficiency. It will be false. Question number 3. In drag type of wind turbines, the tip speed ratio can be greater than 1. Is it true or false? So just try to recall the lambda for your hint.
False, sir.
Okay.
It is smaller than 1.
Okay,
False.
we will check. Okay. Just wait for 1 and 2 minutes. Okay, we know the tip speed ratio is lambda equals to velocity of tip to velocity of wind. Okay, so the tip speed ratio is greater than 1 for the lift type and less than 1 for the drag type. The statement is saying that the drag type of wind turbines, the tip speed ratio can be greater than 1. So it is wrong because for the drag type, it can be less than 1. So it will be false. Question number 4. Two blade horizontal axis wind turbines experience uneven force due to the pressure of tower. Due to the presence of tower. Sorry. Is it true or false? I think we have covered this for many times. You can easily answer. Try to recall our discussion on fatigue. Maybe you will get the answer.
False.
Okay. Anyone else having some other opinion? Read the question carefully. A two-blade horizontal axis turbine experience uneven forces due to presence of the tower.
This is
Sir,
true.
true. Because 3
True.
blades will distribute the load efficiently.
Okay, right. So we are
Presence
having
of the
two.
presence of tower makes the difference.
Okay, so we are having two opinions for true and one is for false. Okay, let's again. Whoever saying the false, please rethink because majority is saying the true. Try to rethink.
Because balances now one tower, one blade is going to balance another one.
No.
Directly opposite.
It's not about the weight. You are not balancing the weight. Actually, we have discussed it. Okay, I will again discuss. One blade is like this. One blade is like this. This is location A, location B. So one blade is having tower behind that, and one blade is not having tower behind that. So in every moment, this situation will come.
Yes, in one particular location it will not balance. One particular.
Yeah. Yeah, that is the location, na? Presence of tower. So that is the
Yes.
location. It's mentioned in the question, presence of tower. So only at this location
Yeah, that will
we are
not
dealing.
will.
Yeah.
Yes.
Yeah. So now all three are agree. So the two blades horizontal electric wind turbines experience uneven forces due to presence of tower, because at this location you can see at B location tower is behind, okay, as compared to the A location. Okay. So at A the wind is freely move around the blade, but at B the tower will block the wind after the blade. The loading will be different. Okay, so this will generate the cyclic loading. But if we are having three blades, then what will happen? The loading will balanced by these two blades also. So now the unevenness will be decreased. It will not eliminate. Okay, don't think that the if the three blades they will eliminate the cyclic loading. No, but it will reduce the effect. Okay, so we can it will reduce. So it will increase the fatigue strength of the material. Okay, so the cyclic loading will be decreased. The two blades horizontal axis turbine experience uneven forces due to presence of tower. It's true statement. Question number 5. Modern windmills use blades made of concrete.
False.
Okay,
False.
let's take 2 minutes.
Never heard of concrete plates.
Yeah, right.
It's fiberglass or reinforced plastic.
Yeah, fiberglass and reinforced plastic, right. And what is the purpose of fiberglass? If you can remember.
Lightweight and good enough strength.
Yeah, with strength.
Both uh, compressive as well as you can say torsion also both.
No. The major strength we are looking in the blades. We have already discussed it in our previous question.
Fatigue is due to both the forces acting in both direction.
No, that is fine, but whenever we are finding the strength, then every strength is different actually, na, for material. Because every material behave different in different loading. If you are only compressing a particular material, then it's fine. If you are applying only tensile load, then it will work differently. But whenever you are applying cyclic loading, then the behavior will be completely changed. Okay. So the fatigue strength should be high.
Okay.
So the concrete, they are mentioning the concrete. So actually this question is confusing because we are using the concrete in modern windmills, but for which part we are using the concrete?
The structural part, main structure.
Yeah, for the structure, for the tower. Actually for the tower we are using the concrete. Reinforced concrete we are using for the tower because the tower has to sustain all the loads, all the wind loads, all the dead loads. Okay, so we are using the reinforced concrete for the installation of the towers, so that our we will get the high stability of the wind turbines. So this statement is false.
Yes.
Okay. Now still we have 10 minutes. So quickly we can revise. Okay. Through the questions. If anyone is having any doubts, let me know. So this is the question number 1. These are the answer. Just take 1 minute. Anyone is in doubt, let me know. We will discuss again. Okay, I think there is no doubt for this question. So question number 2 is the answer. There's also no doubt. Question number 3. There is no doubt. Answer is b square. Number 4. There is no doubt. Number 5. There is no doubt. Number 6. There is no doubt. Number 7.
Sometimes Tom velocity is used, sometimes speed is used. Is any relation with the direction? Sometimes.
No,
It is
no. No. It's similar actually.
similar. Now, sometimes velocity used, sometimes
Yeah.
used.
For its ratio actually, it is not having any unit, na tip speed ratio. So tip velocity ratio you can also say, because these are the velocity only, velocity of
No,
the wind. And
I'm not asking for this particular question. In the lecture,
yeah,
also sometimes speed, sometimes velocity is used. Terms
yeah,
are
they are interchangeable actually.
yeah, because direction is also continuously changing. No? Also, when the uh, blade is rotating, direction is changing. So speed may be constant, but direction continuously changing.
So
If
direction is changing, then that's why we are using the bearing, na. So that bearing is also changing the direction of the wind blades. So you can say, you can consider every time the wind is facing for the maximum power. Okay.
so, we
We
are
are
not
having
confused now whether terms velocity we used or speed is used. It's nothing linked with any
nor
direction. Na?
yeah
Not linked.
normally we use tip speed ratio, but
Yeah.
velocity sometime maybe it's called velocity. No, but try to use tip speed ratio.
Okay. Some questions velocity term is used, some speed is also used. In lecture also. I was little bit concerned for this. That's why I asked this question. Otherwise, in this particular question, when the ratio comes, then doesn't matter.
Yeah.
Yeah. Okay. Fine.
Okay. Number 8. The answer. No doubt. Number 9. Doubts. Number 10. Out. These are the answers for quiz. Okay, I think there is no doubt. So also time is over. So I'm closing the slide.
Okay. Thank you. Right.
Okay, thank you everyone for joining. I hope
Thank
you will join in next class also.
Yes, sir. Definitely.
Yeah.
Yes, sir.
Okay.
Thank you.
Okay. Thank you very much. Thank you. And for others, I will provide the recording. NPTEL team will provide the recording and this PPT. So you can access the recording and PPT through the link the team will share. Okay. Thank you very much.